Just give me that. Yeah. So, a very good evening. Uh, welcome to the second week interactive session on geosynthetic and reinforced soil structures. In the previous week, we had gone through the topics, through the basic introduction of the types of geosynthetics and what are the functions of geosynthetics. In this week's session, we will be discussing some of the testing, different types of tests, how to test the geosynthetics, those things, and we'll be also discussing a little bit on the mechanics or the concept behind the reinforced soil structures. All right. So along that way, we will be solving some problems, very small number problems. So mainly this week's ones, first week, second week, third week, these are generally descriptive type. So there are very less problems. So what we will be doing, we will be just revising the theory content, and then we will solve some very easy basic problems. Okay? And if there is any issue, then we can discuss. So let us start. Okay. So first we have our triaxial compression, right? So in the previous class we had solved some problems regarding the triaxial compression test, right? So in the triaxial compression test, we know that there are different types of triaxial compression tests, CU, CU, CD. So we solved some problems from CU test and CD test. We determined the C and phi values from the triaxial test data. All those things we had solved in the previous class. So, so now here we will be actually looking into the triaxial compression test of reinforced soil specimens, right? So a soil which is previously we are just looking into simple virgin soil, right? But now we are reinforcing that soil with certain geosynthetic material. All right. So now, obviously, due to this reinforcement, the strength of the soil will increase, isn't it? That is our only purpose. The purpose of introducing reinforcement is to increase the strength of the soil, right? So, so in order to determine the strength of the reinforced soil, we will be looking into this part. Okay, we will look into that in this part. So, as you know, triaxial compression tests are conducted on cylindrical samples, right? So the important parameter of that sample, physical property of that sample is the height to diameter ratio. So can anyone tell me what should be the height to diameter ratio for a triaxial soil sample? What should be the H by D ratio? Anyone can just turn on their mic and just answer. What should be the H by D ratio? What is the criteria for the height to diameter ratio? What should be the H by D ratio for a triaxial compression test? Please, any one of you can answer, right? It's very easy also. You all of us have done the soil mechanics course. All of us have probably done the triaxial tests during the soil mechanics lab. So we all know this. Right? So what should be the optimum? What should be the optimum height to diameter ratio? It should be it should be almost equal to 2 or say greater than 2. Okay. So the H by D ratio should be about 2, around 2. Now, what is deviator stress? So we apply, so when we apply the loading on the triaxial specimen, that loading is actually nothing but the deviator stress. So we have the triaxial specimen like that, right? So this this is sigma 3, or the confining pressure, which is acting all around, isn't it? Now what we do, we apply some, we are applying some axial load. So that axial load is actually nothing but the deviator stress. The deviator stress is nothing but sigma 1 minus sigma. So sigma 1 becomes sigma plus sigma. Okay. So this is our deviator stress. Nothing but sigma 1. Now to plot the simplified, say, this more on envelope, also to find out the CN5, what we do, we plot the PQ plot. Okay. So we plot the PQ plot. In the PQ plot, uh, this P is nothing but our, this is the PQ plot. So the P is nothing but the mean stress, right? So P is the mean stress, is nothing but 6, right? The average of the stresses, principal stresses. And Q is nothing but the shear stress. Okay, so we plot that, we get some line, and here we get some angle, and A. From that we can find out phi. From this we can find out C. Okay, now next is the normal stress. So when we have a specimen, the specimen will have some uh, failure plane, right? Okay, we will have some failure plane. So in that plane, and say not failure plane, there is any plane. So any plane on the sample, there will be a normal stress acting and one shear stress, right? So what is the normal stress on any plane? Is plus sigma 2 plus sigma 2 cos plus theta. And what is the shear stress? Sigma 1 minus sigma 2. Okay. Now, one more important thing is the inclination of the critical plane or the failure, the plane along which the sample is going to fail. So that is going given by 45 plus, okay, 45 degree plus 5 by 2. We already solved problem with this in the previous class, if you can recall. All right. So now the basic equation which comes by taking the equilibrium of the soil or from the Mohr circle, and we have used this basic equation to solve the problems in the previous class, and that is nothing but sigma 1 f 1 plus sine phi. It can be also written as 10 C 10 40. What is this? Is nothing but K. Okay, the coefficient of basic partition is equal to KP plus root over KP. Okay, so if we see this stress result, okay, so there is a there are, we have tested many soil samples. So we have tested the unreinforced soil sample, and then we have reinforced the soil with single layer of reinforcement, 3 layers of reinforcement, and 5 layers. So obviously, intuitively, we can say that if the number of reinforcement is more, the strength of the soil will be more. So hence you can see that as we increase the number of layers of reinforcement, the strength of the peak strength of the soil is increasing, right? So this is for the unreinforced soil, and this is for the soil reinforcement with 5 layers, right? Now this is for the test on low confinement pressure. So what will happen if we increase the confinement pressure? So if the confining pressure is very high, so we will see that the difference between the unreinforced and the reinforced specimen uh, is not that large, right? The influence of reinforcement actually becomes very less. Okay, so if the confinement is very high, the confinement pressure is very high, the influence of the reinforcement is lesser. Okay. Now the increase in the strength. So we just now we saw that if we reinforce the soil specimen, just now we saw that if we reinforce the soil specimen, the friction and the strength of the soil is going to increase, correct? So if you are reinforcing the soil specimen with a number of layers of reinforcement, the uh, strength of the soil is going to increase, correct? So this increase in strength of the soil can be like explained or can be looked into from two aspects. One is the increase in friction angle of the soil, or the appearance of an apparent cohesion. So these are the test results shown here for, say, for a granular soil. Okay, cohesionless sand, say sand. Okay, sand species. So obviously what will happen is that the strength of the soil is going to increase. This increase in strength of the soil can be explained in terms of the increase in friction angle. So initially it was phi, and then it became phi r. So phi r is obviously greater than phi. So one more way it can be explained is that the development of apparent cohesion. So the soil initially has cohesion of 0, but what happens due to the increase in strength? The increase in strength is due to the development of an apparent cohesion. Okay, so we'll see this. We'll see in the next slides, that in the upcoming slides today, that when when does this increase reflect in terms of this increase in friction angle, or when it reflects in terms of this increase in apparent cohesion, the concept of apparent cohesion. Okay, so there are two cases. In those two cases, in one case it reflects in terms of this increase in friction angle, and in the other case it reflects in terms of apparent cohesion. All right. Okay. Now, what are the things that actually influence, okay, the strength of this reinforcer? So the things that matter are the spacing of the reinforcement, right? So we sorry. So what we are doing, we have a soil mass. So what we're doing, we are placing some reinforcing material, right? So we're reinforcing the soil. Sorry. We're reinforcing the soil by placing some spacing by placing the reinforcement in some layers. So this spacing of reinforcement actually influences the strength. Okay. Then the next thing which influences the strength is the strength of the reinforcement. Okay, the strength. So these are some, say, some geotextile or some geogrid, right? So the strength of the individual geotextile or so whatever geosynthetic values, the strength and the stiffness of the reinforcement, this influence the strength of the reinforcer, right? And the third thing which influences the interaction between the soil and the reinforcement. So here above we have soil, here we have soil, right? So the reinforcement is sandwiched between the soil layers. So there is some development. There is a development of friction and friction. There is friction between the soil and the reinforcement, right? So that interaction in terms of this friction or the shear which develops between the soil and the reinforcement, that actually influences the strength of the reinforced soil, right? So uh, say you have a geogrid. Okay, say you have a geogrid. Say you have a geogrid, and say you have larger, say larger size, not sand, say larger size granular material aggregates placed on the top and on the bottom. So what will happen is, if this due to geogrids have large open spaces right in between them, they have large open spaces. So what will happen? There will be some interlocking uh, between the geomaterial and this geogrid, right? So geometry that gravel will be getting inside that aperture. So there will be some interlocking. So so what will happen? That frictional resistance or the say the friction angle delta between the reinforcement, that is the geogrid, and the geomaterial, whatever soil or that gravel, okay, that we are reinforcing, that will increase. Okay, that will be large. So in this way, these things actually influence the strength of the. Okay. Yeah. And the spacing actually, see, the spacing, what happens is that if say the spacing is very less, the spacing is very less, what will happen? The shear force between the soil and the this soil and this reinforcement, the shear force between the soil and this reinforcement won't get mobilized properly, right? If this is too near, this reinforcement there are too near, then it won't get mobilized properly. And if the gap is too much, what will happen? The failure will actually occur. Failure of the soil will occur at a region which is not like between these layers in the virgin soil. So this reinforcement will be useless. So this spacing should be properly determined. Okay. Now the failure modes, right? So the failure can happen in two modes. One is the pull out failure, okay, the pull out or the sliding failure, and the other one is the rupture failure, rupture, or you can say tearing, whatever. Okay, so pull out and rupture, these are the two modes of failure. Pull out means what? See, you are placing reinforcement sandwiched between two layers. Pull out means the reinforcement comes out, okay, so comes out of the soil. In that way the failure happens, that is the pull out. The rupture is what happens, the reinforcement tears. So due to high loads on the reinforcement which is there between the soil, high load, what happens? There is tearing in the reinforcement. Okay, the reinforcement ruptures from between. Okay, so these are the two modes in which the failure can happen. One is the pull out and one is the rupture. When pull out, what happens? Pull out happens when the reinforcement slide out. Reinforcements and the soil separate by sliding. That is the pull out failure. The rupture is when there is tearing of the reinforcement. Okay. Now when will which failure, right? So say we have a soil mass, right? So we are putting some reinforcement. Say this is the embedment length. So this all these things we will be actually starting. Okay, later. This is the shear force developed mobilized at the interface of the reinforcement and the soil layer. Okay, and say some normal pressure is of the soil. Okay. So this shear resistance which develops is nothing but two times because there are two faces, top face and the bottom face, two times sigma v into length into width into tan delta. Delta is nothing but the interface friction angle. Okay, the interface friction angle is the friction angle between the soil and the reinforcement. So how can we, one thing can come to a mind, how can we determine this? So you must be knowing our direct shear tests, right? So direct shear test, from direct shear set, what we do? We find out the CN5 or the 5 value, CN5 value of soil, right? By shearing the soil over a predefined failure plane. Similarly, big direct shear boxes are available where what we can do, we can conduct this direct shear test between the soil and the geosynthetic material, maybe geotextile or geojet, whatever. So from this direct shear test, this delta value can be determined. Okay, this delta is what? What is this delta? This delta is the friction angle between the reinforcement and the soil. Okay. Now, if this mobilized shear resistance, the shear resistance which developed at the interface of the reinforcement and the soil, if this RP is greater than the ultimate tensile strength, okay, so this geosynthetic material will have some tensile strength, right? So if you keep on pulling that, a moment will come when it will break, right? So that is the ultimate tensile, the tensile strength. So if this RP or the mobilized this shear resistance is greater than the TU value, then what will happen? It's just common sense, right? So what is going to happen if it's more than TU? If it is this more than TU, then we'll have pull out fee. Okay, okay. So pull out will govern the this is going to the reinforcement is going to slide out, and if say this TU, just a second. This should be actually, if I repair it, just write it in T. T. Okay, so if TU is greater than RP, right? So strength of the reinforcement, the tensile strength of the reinforcement is higher than this mobilized shear force, right? If that is higher, then obviously there are no chances of the rupturing of the geosynthetic, right? TU is higher, right? So TU is 20 kilonewton per meter, and this mobilized friction is 10 kilonewton per meter. So obviously there are no chances of rupturing. Okay, this won't rupture, so the failure mode will be pull out. In that case, the probable failure mode will be pull out. And say this TU is less than R. Okay, so RP is higher, the mobilized resistance shear force is higher. Then what will happen? There is a possibility that the this geosynthetic material won't be able to take that load, and it will just rupture. Okay, so this is the uh, sorry, the rupture. Okay, the rupture. So if the mobilized force, the shear resistance developed is less, if the shear resistance developed is less than the ultimate tensile strength, then what will happen? Pull out. And if it is higher, then there will be rupture. So just by common sense sequence, right? Obviously, the force acting is higher than the tensile strength. So what will happen? This synthetic material is going to break, so there will be rupture. Okay. Otherwise, there will be pull out. Okay. Now, so we had studied the equilibrium analysis of the soil wedge during the class. So we took this soil wedge, okay, and then we did the equilibrium analysis, and from that we got this basic equation, right? So where we have the relation between the this major principal stress and the minor principal stress, right? This is the major principal stress. This is the minor principal stress. Okay, and you can see a term here, summation of T. Okay, so what is the summation of T? The summation of T may be governed by pull-out failure or may be governed by the rupture failure. Okay, this will change with the mode of failure. So if the mode of failure is pull-out failure mode, the summation T will be different, and if the mode of failure is ruptured failure mode, then the summation T will be different. Okay, so if the failure mode is rupture failure mode, then this is going to be Tu cos theta. Okay, so what is SB? What is SB? This is the vertical spacing. Okay, so this is the vertical spacing of the ring, right? And what is this whole term b cos theta by SB? Okay, this, see, you can see b cos theta is what, this length, and SB is what is this thing. So this will give the number of reinforcement layers. Okay, so this is the number of reinforcement layers that is cut by the failure wedge. Okay, so say you have a soil here. Say the failure occurs like this. So these are the number of reinforcement layers that are cut by this failure wedge. Okay. Now this is in the case of tensile or rupture failure. And what will be the case in yeah, what will be this in case of the pull out failure? Is nothing but 2 sigma 1 2 because top and bottom mu sigma cos theta by. Okay, so this mu is nothing but the interface friction coefficient, is nothing but 10 delta. Okay, dr is nothing but the width. And this sigma 1 is the this major principal stress. Now what we can do, we can replace this delta T by these two values of two expressions for summation T, and we can get two different cases. One is for rupture failure, one is another is for sliding failure. Okay. Okay. Now when now if rupture governs, okay, if the rupture happens in the geosynthetic material, okay, in that case where the probable failure mode is rupture, okay, understand this thing, when the probable failure mode of the reinforced soil is due to rupture of the geosynthetic material, in those cases the increase in strength of the reinforced soil is explained by the apparent cohesion. So please recall that we had studied, right? We had studied that there are two explanations, right? One is due to increase in friction angle, and the second is due to development of the apparent cohesion. Okay, so now if there is failure due to rupture, then which explanation governs? This apparent cohesion explains the increase in strength. Okay, and this apparent cohesion C is given by du by 2I6V root over K. After that, we will be solving some problems, right? And I won't be so today you will be solving, right? I will like please try to solve, then I will solve. Okay. Next, we have what will happen if the pull-out failure governs. So if the pull-out failure governs, then the increase in friction angle actually explains the increase in speed. Okay. So in that case, the increase in friction angle is pi r, you get it greater than 5, and this can actually be determined from this changed Kp value. This changed Kp value is given by Q by 1 minus 2r. Okay, so then you can equate it to 1 plus pi r, 1 minus sin pi r, and from that, from here, this equation, you can get this pi r value. Okay. So obviously denominator is less than 1. So this Kp bar will be greater than Kp. And if Kp bar is greater than Kp, then this pi r will be greater than pi. Okay. Just this. Okay. Okay. Now, when the confining pressures are low, okay, so in the field, what we have done, we have constructed a reinforced structure. In the structure, this confining pressure, which is coming, the minor principal stress, which is getting generated, that is actually low. Okay, so what happens at low confining pressures is pull-out failure governs. Okay, this pull-out failure governs when the confining pressure is low, and at high confining pressures, this rupture failure occurs. Okay. Now, what is that value of this confining pressure or this minor principal stress below which we have pull-out failure and above which we have rupture failure? So that is the limiting confining pressure, and that is given by this equation. Okay, so if sigma 3 is actually less than this value, then what will happen? Pull out failure. And if it is more, right, then rupture failure. So you can just visualize it, right? Obviously, if this confining pressure is higher than the this RP which we had discussed, that will be large, very large. The chances are that that will be higher than the what? That will be sorry, that will be actually uh, yeah, that will be actually higher than the tensile strength, right? So if the confining stresses are large, then what will happen? That mobilized shear resistance that will be much, that is expected to be much higher than the tensile strength, the ultimate tensile strength of the geosynthetic material. What will happen? There are chances, more chances of rupture. Okay, so this is like, these are very intuitive things, right? Those intuitive things are actually expressed in term mathematically, okay, with the help of the concepts of soil mechanics. These things are basically very intuitive, isn't it? Okay. 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 Now we have a problem. Okay. Given Q is 30 kilonewton per meter, okay, the ultimate tensile strength of the geosynthetic material is 30 kilonewton per meter. The phi of the soil is how much? 30 degrees. Okay, the spacing of the reinforcement is 0.5 meters and the width is 0.65. And this mu, this mu is 0.6. That is the friction coefficient between the what? Between the soil and the geosynthetic is 0.6. See, okay. Then if confining pressure acting is 200 kPa kilopascals, which type of failure will happen? Accordingly, find the apparent cohesion or the increased friction. Okay. First, we need to say which type of failure is going to happen. Okay. So please solve it. Please solve this problem. How are you going to approach it? Please solve. Try to solve.
Hello. Hello.
Yeah.
Equal
Uh,
to 1 plus
it's not
10
clear.
pi by 1 minus 10 by.
I'm unable to understand.
That such we find the passive coefficient Kp.
Which one? First we find the
Kp.
Kp. Yeah,
Yeah.
yeah. First we
1
find the
plus
Kp.
sin
Yeah. So
pi by
one
then
plus
1 minus.
sine phi by 1 minus sine phi. So 1 plus sine 30 by sine 30. So it will be 3. Okay. Then after that,
C. Apparent coefficient equal to Q by 2 Sv Kp. Root square root of Kp.
which one you are?
C apparent uh,
Yeah,
apparent
you are.
coefficient C. Yeah, is equal
No,
to Tu
no. You
by
are say okay. I understand. You are saying that
uh,
you are
uh,
directly. So my question, first question. Let us answer the first question. So which type of
yeah.
failure is going to happen? Is it tensile failure? This is a rupture
Uh,
failure or the pull out failure?
hmm. This step pull out failure.
No.
Uh,
If it would have been pull out failure, then why are you finding out apparent cohesion?
hmm.
It is the question, right?
Then
See, if the
here
yeah, if the failure is pull out, then this
uh,
increase in friction. First we need to identify which type of failure is probable. Is it pull out failure or is it tensile failure? And based on that, we have to find out either apparent cohesion or the increase in friction. All right. So first, let us answer the first part. Which type of failure will happen? So what should be the approach? How to determine that?
if it is RP is greater than TO, it is
Yeah.
pull out failure.
Okay. But
Then first,
RP, see
yeah,
RP, how to find out RP? RP cannot find
yeah.
out. Right? You are
RP,
right.
then
What is the just now we had studied just now. Just now we have studied that thing. How can we see the confining pressure acting on the field is 200 kP. Based on that, we need to judge, right?
yes.
So how can we judge that? We need to compare with compare this with something.
You have to compare only with the TU and RP.
See,
So,
forget about RP. What is the other thing? Just now we have studied that. RP we cannot determine here, right? See,
then
we studied this, right?
yeah, 2 into
This
sigma.
limiting confining pressure. So if this sigma 3 is less, then pull out failure happens, and if it is higher than this sigma 3, then rupture happens. So let us find out this limiting confining pressure. Okay. So sigma 3 limiting. Let us find that out. Tu is 1 minus 2 by 2br negative. So we can find this out, right? So let us please find out. Please put all the values. 1 minus 5. So how much will be this? Please calculate this one. This is nothing but 106.7 kPa. Okay. Okay. Now, if our sigma 3, if the confining pressure acting is less than this value, then frictional failure occurs. Right? That is the pull out or the frictional failure occurs. So our 200 is obviously not less than 106, isn't it? This 200 is not less than 106.7 kPa, isn't it? So which mode of failure will occur? Which is the mode of failure that governs? It is the rupture failure, right? So if the failure is by rupture, so the apparent cohesion, that concept will actually govern. So now we find out the apparent cohesion. Okay, it is nothing but this Tu by twice Sv to work it. So 30 by 2 into 0.5 to 3. Think that 51.96. Okay. So understood, right? So frictional, see, how did we actually determine this? We are determining this by equating these two terms, right? Yeah, cos phi. So if this condition is satisfied, then what happens? Then we have the pull out failure. Then pull out failure. Okay, so from that condition we determine this sigma 3. So if sigma 3 is less than sigma 3 satisfies this condition, the sigma 3 is acting in our field. Okay, the sigma 3 that is acting in our field satisfies this condition, then there will be pull out. Okay, then there will be pull out failure. Otherwise, it will be this rupture failure. So in our case, this 200 is acting on the field, so that is obviously less than greater, not less than, it is greater than this limiting sigma 3, right? That's why this rupture will govern. So as rupture failure governs, we can find out the apparent position. Okay. And similarly, let us solve this problem. So we have some values given. Now, if the confining pressure acting is 50 kPa, which type of failure happen? So please calculate this. So let us tell first. Please tell me what is the mode of failure that is going to occur. What is the probable mode of failure? Okay, please calculate this one. Please solve this one. Please calculate. U is 20 kilonewton per meter, pi is 30, SP is 0.5, PR is 0.05, mu is 0.06, and the confining pressure acting on the field is 50 kPa. So what is your calculation? So as per your calculation, which type of failure will happen? Please calculate. Same, similar to the previous one. So first, what you need to do, you need to find out the limiting confining pressure, limiting sigma 2. So please find that out first. Please calculate. Same as the previous one. What we need to do, we need to first determine the Kp is same, Kp is 3. Okay. Then what we need to do, we need to determine the limiting sigma. Please calculate. Please tell me what will be the limiting sigma 3 value. What is going to be the limiting sigma 3? Same, okay. Same as the previous one. Sigma 3 is mu 1 minus twice. So what is the sigma 3 limiting? Please calculate. 70. Now the confining pressure acting like in our conditions, in our testing conditions or where we are applying that, it is very low confining pressure. Okay. Okay. So the where in our test or the testing condition, test conditions or where we are applying this user well, the confining pressure acting is 50. So 50 is less than 71.11. So which type of failure will happen here now? Which type of failure is prevalent? This type of failure might happen. Might. Okay. What are the chances there?
Rupture.
Rupture failure, right?
Yeah.
Rupture. So rupture means we can find out the increase in friction angle. So for that, what you need to do? We need to determine Kp bar. So Kp by so please find that this out. Please find this out. Then this Kp bar is equal to 1 plus sin pi r by 1 minus sin pi. From there, we can calculate sin pi r to be something. So this should be 4.6 now. Okay. So pull out. See, or remember this pull out failure occurs when when for strength high strength reinforcement or low pressure. Okay. And this rupture failure occurs low strength reinforcement or high uh, pressure. This high and low confining pressure, these terms are relative. This high is respect to what? High means high with respect to this limiting case. Low means what? Low with respect to this limiting case. This is the thing. Everything is relative. Okay. You cannot absolute like you cannot compare them absolutely. Just a second. Okay. Here rupture occurrence, right? rupture properties. And here we will have pull out failure, not rupture. So depends. We have okay. So at high confining pressures, and for higher strength of reinforcement, we can see we are having rupture. So if you see this of lecture 16, okay, not like lecture 18, and wait just a second. If you see like slide number 17 and slide number 18, slide number 17 and slide number 17 and slide number 18 of lecture 5, you will see it's clearly mentioned, and clearly mentioned that for low strength reinforcement at high confining pressure, we have rupture. So here the confining pressure is high, so we are having rupture. And if there is the confining pressure is low, so at low confining pressures or for strong reinforcement, so here the confining pressure is low, just 50 kPa in the feet, so hence we are having this pull out or the friction activity. Okay, so numerically also we saw the same results, right? Just think about these things and solve it again, okay, and be more clear, be more clear when there is rupture failure, when there is our pull out field. Low, remember this, low confining stress pull out, high confining stress rupture. Okay, low confining pressure, always remember, low confining pressure pull out, high confining pressure rupture. Okay. Then you have the Haussmann approach. The Haussmann approach is nothing but a different point of view to just look at this explanation, to explain the a different, just another point of view to explain the increasing strength of the reinforced soil. Right? There's nothing, just a different point of view. So here, what we are looking at, we are actually looking at in terms of the reduction in confining pressure. Okay, say this was the initial Moore circle for the sand reinforced soil. So what happens? So initially say it was 5. So due to this reinforcement, this 5 will increase to 5R, right? So this Moore circle will change like this. So it is explained that say the ultimate tensile strength is same. So this can be explained in terms of this reduction in this sigma. Okay, this is known as sigma. So just a different point explanation. Okay, just different view to explain these things. Nothing else, nothing more than that. Okay, that's all, nothing more. Here the explanation is that say due to reinforcement, what happens is that some there extra confining pressure is actually increased. That's all. Nothing else. That is the explanation. And due to this 5 increases or there is development of this apparent equation. That's the explanation. That's all. And in your assignment, I think there are 1 or 2 problems this week assignment related to that. So I hope you will be able to solve this. Okay, so this part is actually over. Now next we will be moving to the testing part. All right. Okay. So why do you need to test? What is the need of testing? So first need is to how do you do this? Identify the product. Say you are some supplier has given you many types of geostatistics, many types of geotextile maybe. So you need to identify the type of the geostatistics. So what we need to do? We need to do some tests. So first is the identification. Next is to select which type of product will be actually suitable for your usage. So there are many usage sites. So if you can recall, we had studied many functions of geosynthetic, right? What were they? Reinforcement, separation, drainage, then filter, then barrier. So many things we had studied, right? So, so say we need to use that for some specific purpose. So for that, we need to choose some specific type of geosynthetic material. And to aid our selection, which geosynthetic product to select? Okay, which product to select? So one is broad type. Say first, say you need to use a geosynthetic as drainage material. So you choose say some geotextile. So you decided that you have decided that you will use geotextile for your drainage purposes. Okay, so you need to solve drainage issue. So what we did first to identify the issue. So the issue is I need to solve the drainage issue. Done. Identification of issue is complete. Second is identification of the product. So which using which product do you want to solve the issue? Which geosynthetic do you want to solve the issue? Is it geotextile? Is it geonet? What is it? So say you have decided that you will be using geotextile. Okay. So the type of geosynthetic you have decided. So first you identified the issue, then you decided the type of geosynthetic that you're going to use. Done. The next thing is that which type of geotextile are you going to use? Okay, which geotextile are you going to use? So in order to answer that question, what you do, you conduct certain tests. Okay, so that's why you need this testing. Next is quality control. Obviously, during the production stage, you need to ensure the quality of the product. So quality control, quality assurance. That means whatever your product you are using in the field, that is pertaining to the design standard. Okay, that is the quality assurance. That's all. And then we have some important standards. So ASTM, this D4354 is the like the basic, the most fast this code for the testing of geosynthetic material. Okay, so these are some of the various ISO, IS, and ASTM standards that are used. Then next come now let us come to geotextile, right? So there are various types of properties. One is physical property is related to the physical means. What physical means related to the say opening size, this all this weight, all these things like mass, like all these things. Those are the physical properties. Then we have the mechanical properties. So what are mechanical properties? Mechanical properties are nothing but the strength properties. What is the strength property? Tensile strength, main tensile strength, like the rupture strength, the tensile strength. Okay, that is the mechanical property. Then we have the hydraulic property. What are the hydraulic properties? That is the permeability. Okay, the permeability can be of two types. One may be the in plane permeability, say flow when the flow is along this plane, laminar flow. Okay, or this in this plane. Okay, planar flow. Okay, that kind of flow or the cross plane. Okay, the flow is like this. Water flow is like this. So two types of permeability, in plane and cross plane permeability. Then you have the endurance properties. Endurance property means say repeated loading or in the field there will be some wear and this installation like say boulders will be placed over that is material whatever. So that is related to the endurance. The last one is the degradation property. Degradation property means along as time passes, the geotextile is say exposed to this weather, right? So weather is exposed to weather, sunlight, many things, aberration. So due to that, what happens? There is degradation in the geotextile. So that is the degradation. Yeah. Now physical properties. Okay, so physical properties. See, the physical properties mainly are the specific gravity, the mass per unit area, the thickness, and the stiffness. So specific gravity, what specific gravity is. Okay, so this the weight of that weight of that substance, the weight of the uh, uh, what ratio of the weight of that substance to the weight of the weight of water of that same volume of same volume, right? With that same volume, that is nothing but a specific. Okay, so there are various methods using which we can determine the specific gravity. So mostly it is determined by pygnometer or this density bottle. Okay, so there are some typical values of the specific gravity that are of some materials. Those were given to you. So try to remember that. So if you notice this polyethylene, polypropylene, these are specific gravity less than one. That means this is floating water. Okay, so the geosynthetic material, those are made with to test the geosynthetic material that are made with this type of polymers. They also some sinkers have to be used so that we are able to submerge those things in water. Then we have mass per unit area. Okay, so you take some specimen, you take the mass, and then you take the area. So just the mass divided by the area of that specimen will give you the mass per unit area. Okay, so all ASTM codes are available for all these things, right? Then we have the thickness at a certain pressure. At a certain pressure, what is the thickness of the geotextile? So obviously, if you increase the pressure to large, this thickness is going to reduce, right? So at a certain standard pressure, what is the thickness? Then you have the stiffness. Stiffness. What we do? Stiffness is nothing but the this interaction between the weight and the this bending stiffness. So what we happen, we have a predefined inclined plane. In the inclined plane, we stretch the geosynthetic and we measure the overhang length, right? So what we do, we place the geosynthetic here, we measure this overhang length. Then, yeah, after that it drops. That. So using this length, what we can do, we can determine the stiffness of the geosynthetic material or the geotextile. Then we have the mechanical properties or the strength properties. So first we have this uh, compressibility. Okay, so compressibility is nothing but with the increase in pressure applied stress, how much this thickness changes. Okay, how much the thickness of the geotextile changes. So you can see for non-woven. Okay, so non-woven, obviously non-woven, you have seen, if you remember the image of the non-woven, uh, if you know coir, right? Coir geosynthetic, those things are generally non-woven. Okay, so for non-woven, this compressibility is very high. You can see as we increase this applied stress, what happens? There is a rapid reduction in the thickness of the gypsum. Okay, and for woven geosynthetic and this heat bonded non-woven geosynthetic, we can see that the compressibility is very low. The thickness doesn't change that much due to the application of pressure. Okay, then we have the trapezoidal test. So in the trapezoidal test, what happens? So we have a geosynthetic sample. Okay, there is a cut of 25 mm made here, and these clamps are attached. Okay, trapezoidal clamps are attached here, and these are pulled apart. Okay, so with that, what we get the tear strength. Okay, means the load at which the geotextile completely tears the ruptures. Okay, the result is reported in 4 seconds. So let me just show you this next, and I will show you the video. Then we have the grab tensile strength. Okay, so grab tensile strength, you can see this is the geosynthetic material, and this is actually grabbed between these clamps, and it is pulled. Okay. It will fail and it will rupture at some point. That will give you the ultimate tensile. This is the grab tensile. And then we have the punching stress, punching strength. The punching strength, what has happened? We have this one geosynthetic material here, and we have this plunger. So this plunger is slowly pushed into the geosynthetic material, and this load is actually measured. Okay, and this CBR puncture test is one more punching stress thing where the CBR mold and the CBR plunger is used. And another most important test is this dynamic puncture test. In this dynamic puncture test, what we do is that we take the geosynthetic when we drop, drop drop this cone. Okay, drop this point pointed cone of a like standard. There is a standard size. There is a standard width of that cone. What we do, we drop that cone over that uh, geosynthetic. Okay, so this cone is that we will drop it. So what will happen? Obviously, that will go inside the geosynthetic and make a hole. So what we do, we measure the diameter of the hole made by that cone. Some device is there, so putting that measuring tool, we can measure that diameter of the hole that is made. Okay, so the larger the hole diameter, the larger is the construction damage that is. And one more thing, important thing is the seam strength. The seam strength means what? So what will happen? So geosynthetic, you cannot measure of geotextile, you cannot measure of infinite length and width, right? So there is some predefined the specific width of geotextile that comes from the manufacturer, from the factory, right? So what will happen if you have a large area? We need to steam it. We need to stitch the geotextile. Okay, so the seam strength is nothing but the strength of that this seam, seam or the stitching that you are making. Okay, okay. Now let me just go just a second. Uh, so here, see, you can see this trapezoidal test. Okay, so initially, see, it's not clear here. So initially there is a small cut made here, and this then these clamps are pulled. Okay, you can see there is rupture of this geotextile. Okay, so like this we have the rupture. All right, so this is not actually very visible. Here if you look here, you can see a small this initial cut is there. Okay, okay. Next you have this grab tensile strength. So see, this is the geosynthetic material that is grabbed between the clamps, and we are pulling. So here in this monitor, you can actually see this graph that is developing, load versus this strain. Okay, okay, so you're starting to pull. You can see it is increasing to maximum it's increasing, the load is increasing, and then it starts to reduce. Okay, as soon as the rupture occurs, so you can see here you can see here. Yeah, okay, shell load is increasing. Then see rupture occurs. Okay, you can just notice the rupture. As soon as the rupture occurs, this graph is falling down. Okay, just notice carefully. Okay, just see here and here. Okay, as soon as the rupture will occur here, just see rupture occurs, this graph falls down. Increasing. See rupture occurs, this also falls. This curves can't stop. Okay. and then we have this thing, this punching shears. See, this is the geotextile. This is the apparatus, and this is the plunger. Okay, this plunger is slowly actually pushed. Okay, this plunger is pushed into this geotextile, and the load is measured. Okay. Share screen again. Okay. Okay. Now see, we have the tensile strength. Okay, tensile strength can be tensile strength test as you just now saw, is gap tensile strength test. So that can be carried out uh, in many with many various widths of geotextile. Okay, we can have narrow strip test with 50 mm width. Okay, 50 mm width, and we can also have wide width test. So wide width test, we have a 100 mm width of geotextile. Now, if you see this graph, you can see that there are five types of. See, there are five types of geosynthetic, or geotextile. Five types of geotextile that have been tested. Okay, A, B, and C show a similar kind of behavior, and D and E, okay, uh, show a similar kind of behavior. Now, tell me, which one would you use for the application as geobags or tubes, and why? Out of these are, say this is group one, and say this is group two. So which group would you choose for the application as geobags or tubes, and why? Which group would you choose for the application as this geobags? Okay, geobags or this tubes for shoreline protection. Okay, for the protection of shoreline, you use certain uh, these tubular bags, geobags or geotubes. So which group of geotextile would you prefer? Group one or group two? Which type of geotextile would you prefer? It be group one, it be group two. Try to think an answer. Even if it's wrong, just guess. Whatever comes to your mind, just guess. Whatever you guess, it should be like calculative guess. You should have some reasoning for that. Why? Which one? Which group? Group one or group two? Which group would you prefer for the application as geobags or tubes for shoreline protection, and why? These were already discussed in the lecture, right? So it should be, you should be able to answer that. Either it is group 1 or group 2. Please answer. There is no issue. Even if it's wrong, what is the issue with that? And try to give the reason. Why are you giving that answer? See, what happens is that this geotextile, these tubular structures undergo large strain, okay, due to deformation and ground movement. So these are facing the shore, right? So there are this soil movement, this soil movement is there. Then these waves are hitting it. So there is huge movement. Okay, there is huge movement. So there are large deformations. Okay? And the force generally developed is quite low in that, but the strain which develops in that is quite high. High strain or high deformations actually uh, happen in them. Okay, they undergo quite a large amount of deformation. Now see this group 1 geotextile, these are kind of brittle, right? At low strain they are rupturing, they are failing, isn't it? At very low strain they are rupturing. And this group 2, these are not that brittle, these are little bit ductile, you can say. Or ductile, maybe ductile is the wrong word. So let us, you understand, right? So they are able to undergo large amount of strain, and after that they fail, right? So for the use of geotextile tubes, this shoreline protection, we should use this group 2 type of this geotextile. It is this DNE, non-woven heat-bond, non-woven heat-response. Okay, either of these, because they are not brittle. They can undergo large strain before failure, before rupturing. Large amount of strain before rupture. Okay. So what happens is that in this geobags and geotubes, the strain is high, but the load is generally very low because these are not completely filled and there is some scope of sag and all. So then generally the this strain is high, but load developed in that in that case is not very high. In that case, we have to choose this group 2 type of this geotext for that case. Okay, then we have this burst strength. Okay, so burst strength. So why is this burst strength test important? What happens is that there might be cases where say there is a large boulder or some large stone or rock, whatever. What is there below the geotextile? Okay, and so it usually like it usually is placed like that. Okay, and there is load from above that, right? There is load from above that. So what happens due to this load? There is chances that this whatever this rock or this boulder, whatever is there, that will actually push and burst. Okay, burst or this puncture into this stone will puncture into this geotextile. You understand, right? Say you are using that to construct pavement, okay, as a separator layer. So you have stones, the boulders there, right? So and you are placing this geosynthetic material. Okay, so this load is acting here. So there might be chances. There are chances that what will happen when the car is moving over the pavement due to the movement in the subgrade, but in the pavement there. what will happen is that due to the pressure, this stone or this boulder which is there below the geotextile, this was rupture out. This was rupture the geotextile from the bottom, right? So in order to test that, this burst strength is test is very important. Okay, so inflatable rubber membrane is actually used. Inflatable membrane is there, and geotextile is there. That rubber membrane is inflated in order to simulate this burst. Okay, so what will happen as the rubber membrane will go on inflating, it will keep on the geotextile above will keep on this deforming, right? Stains will develop and this geotextile will keep on deforming. The moment will come when it won't be able to deform anymore and it will just burst. Okay, it will just rupture, right? So in that way, determine the burst. And then we have the fatigue strength. Fatigue strengthening, say we are using this geotextile in some dynamic conditions, okay, where there are repeated loading, cycles of loadings are there, say earthquake loading, that kind of loading. So in that kind of loading, we also need to test the geotextile, right? So as the number of cycles of loading positive, there are load reversals, right? As the number of reversals are more, the cycles number of cycles increases. What happens? The strength of the geotextile reduces. So in order to quantify that reduction of strength, we do the fatigue strength. All right. Okay. Now next we come to the hydraulic core. Okay. So we come to the hydraulic properties of geotextile. So these are the main hydraulic properties: apparent opening size, cross plane permeability, in plane permeability, gradient ratio, and long term. Apparent opening size is a very important parameter, very important parameter, which specifies the quantifies the opening size of the geotextile. Okay, that is defined by the apparent opening size. So how do we determine the apparent opening size? What we do, we just sieve the material. Okay, we just use that geotextile as a sieve. And what do you sieve? We sieve a specified glass beads or this generally is glass beads of specified size, particular size. We sieve that. We find out same as the sieve analysis which we do with soil, right? Similar to that. Okay, we sieve that and we find out the percentage final. Okay, so and this O95, that is the 95 percentage final size, that is actually called as the apparent opening size, so the O95. Okay, generally it is defined, generally AOS is defined as O95 or O90, these two terms. So O95 means only 5% of the particle is passing through the geotextile. O90 is 10% is passing. So the test may be dry sieving or wet sieving, same as what we do with soil to find out the green size distribution plot. Same, it may be wet sieve or it may be dry sieve. Okay. So what happens? There are chances that if the particle, if this particle size is small, very small, right? So it might stick to the surface of the geotextile. It may clog the pores. That's why wet sieving is preferred. Okay. Okay. Now let us solve this problem. The test result for a woven geotextile is shown below in figure 1. Okay. Can this geotextile be used as a filter if the grain size distribution chart for the soil is shown in figure 2? Okay. So this is the test result for the figure 1 is a test result for the geotextile, and figure 2 is the test result for the soil. Okay, we need to say whether this particular geotextile which you have tested here, which you have tested here, can be used as a filter material in that soil or not. Okay, it is our main target. Now, from figure 1, what you can see, we can find out the O90 and O95, right? So the dry sieve analysis was conducted on this woven geotextile when we got the O95 and the O90 sizes. Okay, so the O90 is 150 microns and the O95 was 230. And on the right side, we have the grain size distribution curve for the soil. Now we are to say that whether this particular geotextile can be used as a filter material for this soil. Okay, can this be used as a filter material for this particular soil? Okay, so if we have gone through the lecture, can you recall what was the design criteria for filter? This was discussed in the lecture, in the week 2 lectures. Can you recall what were the filter design criteria? Anyone can answer, please. You can even see and go through the lectures if we have the lecture PPT or whatever notes you have made. Can you recall what was the filter design criteria? What are the filter design criteria? Can you recall? See, a filter for a geotextile to be used as a filter, it should serve two purposes. One is the fine particles of the soil should not be lost. That is, the fine particles of the soil should not pass through the geotextile too much. Else, what will happen? There are chances of piping. Right? I won't tell you what piping is. You must be doing this from the basic soil mechanics course that you have done. So, due to a filter particle must satisfy two criteria. First is the piping, means the pores must not be that large that the small particles of the soil pass through it. Okay. And the second criteria is the permeability. Okay. The permeability criteria is the pore sizes should be large enough so that the water easily drains out through the geotextile. So two criteria. Piping and this permeability. There are these two criteria. So we have this piping limit where this O90 should be less than equal to the DA, right? Of granulars, and we have the permeability limit where this O90 should be greater than D15 of soil, and this O90 should be also greater than equal to 0. So these are the two criteria, piping and permeability criteria, that should be satisfied by the geotextile to be used as a filter. Now let us check this whether the geotextile is satisfied. So what is the O90? O90 is 150 microns. So O90 is 150 microns here, or 0 mm, and O95 is what? 230 microns, 0.23 mm. All right. Now let us find out the D85 of the inverse soil. So D85 means here approximately here, this one. Okay, so so what is this value? I hope you can read the semi-log graph, right? So what is this value here? What is this value? What is the particle size? What is the particle size?
0.85.
Huh? This one.
Yeah, this one.
Point. See, this is 0.1. This is
Point,
0.2, 0.3, 0.4, 0.5, 0.6. 0.6,
point
right?
6.
So D85 is 0.6. D85 is 0.6. And now please tell me what is D15. D15 is approximately just say approximately. Okay, here this one. This is 0.1, this is 0.2. So 0.15 will be approximately here. So it is definitely more than 0.15, right? This is 0.15. So it is approximately more than 0.15. Say 0.16. Okay, now let us check if these two criteria are satisfied. So is O95 less than or equal to D85? Check. Is O95 less than equal to D85? Yes, right. O95 is 0.23 mm and this D85 is 0.6 mm. So this is less. Now second case is O90 yeah, first criteria O90 should be less than D85. So sorry. So 0.15 is less than 0.6. First criteria satisfied. Second is O90. What is O90 again? O90 is 0.15. So 0.15 should be greater than D15, greater than equal to D15. So is it greater than equal to D15? Yes. So this criteria is also satisfied. Okay, this criteria is also satisfied. So first this criteria is satisfied, this criteria is satisfied. And is O90 greater than equal to 0.05 mm? Yes, right. So all these criteria are satisfied. Hence, this geotextile can be used as a filter material for this. Understood? So this is how we judge the product. Okay. This is why testing is required. See, initially remember while beginning the topic, I told you, say you decided you want to solve the purpose of filter. Then you decided you want to use geotextile. Now you want to decide what geotextile do you want to use. So these are the criteria. This is the criteria that you need to follow to decide which geotextile you are going to use. So this particular woven geotextile, this particular tested woven geotextile satisfies the criteria to be used as a filter. Okay. Okay, done. Next is our cross plane permeability. Okay. The cross plane permeability means what? This is the geotextile. This is the geotextile. So the flow is occurring here through this, like this, right? So this is the cross plane permeability. So this cross plane permeability can be determined by constant head test and the falling head test. So the important parameter here is permittivity. The permittivity is nothing but the Kn by T. T is the thickness of the geotextile. Kn is the permeability. Cross plane permeability is nothing but Q by delta H by A. This is the constant head test. Okay. Q is the volume of water collected. Okay. This delta H, Q is the flow of water. Okay. Flow of water, flow rate, flow rate. Delta H is the head, constant head, and A is the cross section of Q. All right. So next we have the falling head test. The falling head test same. you can write this as 2.3 A delta T log 10 H naught by HF. So HF is the initial height, then head is falling, the head of water is falling, so HF is the final height. A, capital A is the area of flow. Generally, it's 25 mm diameter. This H naught is generally 80 mm. This HF is 20 mm. This A is 25 mm dia. So from that you can find out the area. This delta T is the time taken for that flow, for the head to reduce from 80 mm to 20 mm. That is the time taken for the head to reduce from 80 mm to 20 mm. And this A is the area of water column above the geotextile. Okay. Now let us solve one problem. Okay. So these tests were discussed in detail in the theory lectures, right? So I won't repeat this again. So there are some specified size of specimen, specified normal pressure under which you need to conduct a test. All these things I am not repeating. Let us solve this one. In a falling head test, the head falls from 80 to 20 mm in 200 seconds. The flow occurs across a diameter of 25 mm. Area of water column above the geotextile is 0.01915 meters square. The thickness of the geotextile is 0.5 mm. Find the permittivity and the coefficient of permeability of the geotextile. So please calculate. Just now we discussed the formula. So I hope you can calculate this. Okay. Please calculate this. Head H naught is given, HF is given, time is given 200 seconds. Then area of water of the geotextile is given. Right. So you can find out the permittivity or not. Please calculate. Small a is 0. What will be A? Right. A, then we have delta T, 1 seconds, H naught we have 80 mm, HF we have 20 mm. So you can find out permittivity or not using this relation. Using this relation, you can find out, right? So please calculate. Calculate. Please calculate this. Please calculate.
Hello. Sir,
How much?
no, I have not calculated, but we can use this formula also, no, sir.
Okay.
Permittivity 2
Ah,
by delta H by A.
what?
This we can find the permittivity
Permittivity. This is the
by,
permittivity, right?
yeah, 2 by, yeah, 2 by delta H by delta H into A.
Okay, just let me give the answer. Okay, this will be 0.27 second meters. Okay. Now next, you please find out the permeability, coefficient of permeability K. What will be K? What will be K?
Yeah,
What is K? This one is easy calculation. This
yeah,
this you already have. K you can find out. What will be K?
K equal to permittivity into T.
Yeah. So what will be K? How much?
Yeah. mm.
0.27 into 0.5, it's 0.135, right?
0.017.
0.27 into 0.5. Thickness is
Yes, sir.
0.5. Yeah. So 0.135. Isn't it? So what will be the unit? What is the unit of coefficient of permeability? What will be the unit here? 0.135 what? What is the unit?
Bit unit.
What will be the unit?
per second.
Yeah, per second. Okay. Next, we have the in-plane permeability test. In-plane permeability test means the flow is occurring along this plane. Okay, the flow is occurring along the plane, not cross plane. So in-plane permeability test, the main this parameter which we need to find out is the transmissivity. That is theta. Theta is called the transmissivity. Transmissivity is nothing but the coefficient of in-plane permeability coefficient into the thickness. Okay. So for constant head test, this will be nothing but equal to by I. Okay. So I is equal to delta H. Delta is the head and L is the length across which this flow is occurring. Length of the flow. So the flow is occurring from here to here, say na. So head difference, there is some head difference and the flow will be occurring like this. So this particular length, this is the L. So I you can find it. All right. And this W is nothing but the width of the specimen. So this width. Okay. Now this is the constant. Okay, so another one is the gradient ratio test. So in the gradient ratio test, what happens is that this gradients at different points of the soil and around the this geotextile are taken, and from that we determine the gradient ratio. Okay, and from that, after determining that gradient ratio, we can say that whether this geotextile there is good compatibility between the geotextile and that particular soil. So it is generally you should determine the compatibility between the geotextile and that particular soil which is tested. Okay. Okay. So in-plane permeability test, see, one is this in-plane permeability test, say where say here geotextile is there, see head difference is maintained like that, constant head, and this flow occurs from here to here. So in this case, what happens? The flow is only laminar, right? So it's occurring only in this direction. But generally, it's better to so generally what happens, this permeability or the permittivity or the transmissibility, sorry, the transmissibility can be different in different directions. So for that, another test which is done or which is better is the radial flow test. Okay, in this radial flow test, what happens? This water is head difference is maintained between here and here, and water actually flows from here to here. This like this, water flows radially. Okay, so radially water flows, and in that case also we can determine the this transmissibility. So let us solve one problem for this radial flow test. Okay, so in plane permeability test using radial apparatus, 1 liter of water is collected in 60 seconds. Okay, the head difference was maintained as 300 mm. The outer diameter is 300 mm and the inner diameter is 50 mm. Means this outer diameter is 300 mm and this inner diameter is 50 mm. Find the transmissivity and the in-plane permeability coefficient if the thickness of geotextile is 20. Okay, so let us calculate this. So the outer diameter is how much? 300 mm. The inner diameter is 50. Okay. Now 1 liter of water is collected in 60 seconds. So tell me the flow rate. What is the flow rate? 1 liter in 60 seconds. So 1 by 60 liter per second. So if you convert it to meter per second, please tell me what will be the answer. First tell me, well, in liter per second it will be 0.0167 liter per second. So how much is it in meter cube per second? How much is it in meter cube per second? 1.67 into 10 to the power minus 5. Okay, this into 10 to the power minus. Now this transmissivity theta is given by q ln t naught by t1 twice by delta h. So q is how much? 1.67 into 10 to the power minus 5 ln natural log of 300 by 50 twice by into this head difference. So what is the head difference? Head difference is 300. 300 into 10 to the minus 3 meters. Okay, so calculate this transmissivity. This will be 1.5. Match the, solve it again yourselves. Okay, just check the answers. What will be the unit? What is the unit of transmissivity? What is the unit of transmissivity? You can easily tell by looking at the expression only. What will be the unit of transmissivity?
meter cube by meter second.
Meter cube. What? What is the unit?
That is meter, meter cube by meter second. That is, I think, meter square by second.
Yeah, meter square by second, because numerator meter cube per second, denominator meter, so meter square per second. Okay, then we need to find out the in plane permeability coefficient. Okay, Kp. What will be Kp? Theta by t. So this by t is nothing but 1.587 by 10 to the power minus 3. So we give you 7.93 minus 3 meter per second. Okay. Now we have some other properties. So first is the abrasion resistance. Abrasion resistance means, see, I told you, right? So when we apply some geotextile in the field, say maybe pavement construction or whatever, say we have made a reinforced earth wall, whatever be the case. So in that case, so there will be friction between the soil and the between the geomaterial, whatever it will be soil or it may be gravel, whatever. There will be friction between the soil and the geotextile. So due to that, what will happen? This geotextile surface will get eroded. There will be abrasion. Okay, so due to abrasion, what happens? This mass of the geotextile will keep on reducing. So there will be wearing of the geotextile. So to quantify that thing, this abrasion resistance test is done. So nothing. There is a this sandpaper is used, and the sandpaper is actually rubbed. Okay, so there are approximately 1,000 cycles of rubbing is actually done over this geotextile, and after the rubbing, this loss in weight of the geotextile is measured. Okay, then this abrasion is actually presented in terms of the loss in weight. Okay, so obviously if there is Rubbing, there will be some loss of it. Some material will get where there will be wear of the geotextile. So that is the preparation. So generally it is done by this sandpaper. Okay, in sandpaper, 750 abrasion cycles. So the weight loss in 750 cycles is reported as the abrasion loss. Now next is the durability. So durability means what? Means say how say there will be weathering. So there is weather is going to affect the geotextile material, right? So say seawater or rain, sunlight, whatever, wetting, drying, rain, then sunlight, all these things are going to affect the geotextile, the properties of it. So to understand that, so what we do, we do some wetting and we wet the geotextile and then dry it again, wet it and dry it again. And after those, after doing that, after many cycles, after certain number, we increase the number of cycles and we keep on testing the geotextile. Maybe test certain size strength, and then we see that if the strength of the geotextile is getting reduced or if it is remaining same. That is nothing but durable. Then comes overlay. So what are overlays? Overlays is that what happens generally, we need to construct a new pavement say over old pavement. Okay, so if uh, there is no geosynthetic material between the old pavement, the old overlay and the new overlay. Overlay means a bitumen, right? So between the old overlay and between the new overlay, this is the old overlay, this is the new overlay. So if there is no separation between these two layers, what will happen is the crack which is there, the old crack which is there below the old overlay, that will get transferred to the that will get propagated to the new overlay that you are constructing. Okay, so that is the problem. So in order to solve the problem, what we do, we place a geotextile layer between the old overlay and the new overlay. So here tack coat saturated geotextile is actually used between the old overlay and the new overlay. So that what happens, this crack in the old overlay cannot get transmitted to the new layer that you have just now constructed. Okay, that way what happens, this life of the pavement increases by large, again get increases by large. Otherwise what happens, even if you have invested a huge amount, even if you have constructed a new layer over the old layer, the old crack from below gets propagated to the top. So generally bitumen is coated. See, tack coat saturated geotextile means tack, a layer of tack, it is a bitumen is coated over the geotextile, so that this geotextile also prevents water movement from the old layer to the okay. Okay, now we have geogrid testing. So geogrid testing, the strength tests are quite similar. Okay, similar to this geotextile testing. Okay, here, so in geogrid there are two things, right? One is rib, right? One is rib, and other one is bar. Okay, so one the longitudinal direction, that is the rib, and in this other direction, that is the bar. The fatter one, thicker one is the bar, the thinner one is the rib. So we need to determine the strength of the geogrid or the strength of each rib of the geogrid. Okay, now I have asked here, put up a question here. What is the length or the number of junction criteria for the geogrid tensile testing? So there are two criteria. Okay, one is the this specimen that you are testing. Okay, the specimen that you are testing, that should have a particular gauge length, fixed amount of gauge length. That, and in that specimen, in that gauge, there should be a particular number of junctions. Okay, the junctions between this what to say, this ribs and the this ribs and the bars. Okay, so there are particular number of junctions between the rib and the bar should be present. Okay. So can you tell me what is the number of minimum number of what is the number of junctions that should be present? So this is a junction, this is a junction, this is a junction, right? This is the this is what? This is the rib, rib, and this is the bar, right? So what are the number of junctions that should be present? So minimum three numbers of junctions should be present. Okay, minimum three number of junctions should be present, or you can say the gauge length should be 300 mm. Okay, these criteria should be fulfilled while you do the testing. This strength, the aperture openings and percentage opening, I am not discussing. These are physical properties, very easy. Okay, this strength properties, that is the tensile strength, is important. So, see, so these are the important criteria that you should maintain while testing. Now what we can do, you can test a single rib, you can test, or you can test multiple ribs. Okay, you can test these multiple ribs, you can test both ways. You can test, you can test multiple ribs, you can also test single rib. Okay, you can test in both ways. Okay, now how to get the tensile strength of geogrid, this per meter. So say you are doing this testing, okay, testing of uh, a number of ribs. Okay, so it may be one rib, it may be two ribs, it may be three ribs, it may be four ribs. Okay, here it is one rib, here it's three ribs. There may be any number of ribs that you are testing. Okay, so how to determine the tensile strength of your from that result? So you are testing this, right? So you're testing this, maybe one rib you are testing, or maybe three ribs or four ribs, whatever number of ribs you are testing. From there, you will get a load, peak load, where the geogrid ribs will snap and break. Will get a peak load. From that load, how to get the tensile strength of the geogrid per meter? So for that, what we do, that is equal to nothing but number of ribs per meter width, okay, divided by number of ribs in test, ribs in test into the peak tensile. Okay, so number of ribs per meter by the number of ribs for the test to the peak tensile. That will give you the tensile strength of the geogrid per meter length. Okay, per meter width. Sorry. Now installation damage in geodesy. These are very normal intuitive things, right? So obviously you should consider the damage that will be there. So every installation is not perfect, right? All installations are imperfect. Like in the site, so these geogrids are thrown, these are like kept kept in open area, so there is some so in the during the installation also there is heavy wear and tear, so that like those damage into the installation you should consider while you design, right? So the damage factor should be considered. So in laboratory, what you are doing, you are finding out a tensile strength. So that is under what to say? It is under very ideal condition, right? But in the actual ground, you might not get that amount of strength. Why? Because there will be some damage due to installation or weather or some whatever factors. So that factor you should consider. Okay. So that is what. Okay. So same, so geonets also are same. Geonets also can be tested similarly for strength and other purposes. Same. And then we have geomembranes. So geomembranes, where are geomembranes used? Geomembranes are generally used as linings in canals for landfills and all those things. So testing of geomembranes are also important. So thickness, density, these are all physical properties. And one more important property is the shear and peel strength of geomembrane. Okay, so geomembranes have to be applied in very large areas, right? So canals or maybe this, as I said, landfills. So these have to be these reams of geomembranes have to be connected. Okay, these are generally heat. They are connected with heat. Okay, they are seamed with heat. So there are two types of tests that are conducted: the shear and peel. So one is the peel strength. So this is the joint, the seam, right? So these are sheared. These are the load is applied in this opposite direction. So this gives the shear strength of the seam. Rather is the peel strength. So say you have a two layers of geometry like this, right? So one is peel like this, one is pull like this. So peel strength. Okay, to be like this, to be like this. So those are peeled. So these are peeled. You can peeling, you know, right? Peeling. Those are separated like this. Peeling strength. So that will give the peel strength of the seam. Right? And obviously, the other more important property is the tensile strength, because these undergo large amount of deformation and large amount of forces act when they are used mainly in say these landfills, because of the waste of the landfills. uh, there are these gases which develop. So these gases, they expand. There is some this elongation of the geomembranes, and also the loads of the, see, year after year this dumping is landfills, these waste are dumped into the landfill, right? So due to this dumping, this tensile strength of the geomembranes are very important. So this test, there is normal testing. So what we do, you take and say similar to the geotextile and all these tests, what we do, put in the clamps and you put it and you get the tensile strength. Okay. So geomembrane should actually be have large elongation. They should show large elongation. They should almost show 500% elongation. This is the desired property. So geomembrane should show about 500% elongation before they break. Okay, so done. We are done. So there are just two videos that I will show you. Just like this. Just show you the video. So this is the testing of geogrid. Okay, let us see this video. So see, this is the clamp, and you can see this one rib of geogrid is being tested. Okay, this is one rib. So other ribs are cut. Okay, we are just testing a single rib. Okay, so we are pulling, and then suddenly it will snap. And pulling it, and see it breaks. Okay, so you can see this other these ribs are cut. Okay, you are just testing a single rib here. In this case, we are testing a single. So we just keep on applying the load, keep on pulling it, we keep on pulling it, and it will suddenly snap. Okay, see again, and it snaps. Okay, and here there is a video. Means how these actually geomembranes are. This is a proprietary company, their method. So how these are actually, this is one of the process using which how you can seam or you can join two geomembranes. Okay, so this is done by heat. By you heat it and you heat and apply pressure. You heat it and apply pressure. So what happens? These geomembranes join together. So let us just see a bit. Yeah, you can see using this machine, what they are doing is that they're heating it, and along with that, they're applying some pressure. Okay, using this machine. So what happens with that? It gets these geomembranes get bonded. Okay, so you can see this machine, these are getting bonded. You see, it's so nicely they've gotten bonded. You can see just they act like a single geomembrane there. Okay, so here this is the seam. Okay, this is the seam P1, P2 is written. This is the seam. This is one geomembrane layer. This other geomembrane layer. They have joined it. Okay, so they have cut it for testing. So they will cut this piece, they cut this part, and they will test this the strength of the seam. So they've cut it, and then you can see we are there testing. This is the shearing test. Okay, so just testing. See, this is the joint. Let us see one more. See, this is one geomembrane, this is other geomembrane. Okay, this is joined here at this portion. You see, it will snap from here. At this part, it will snap. You can see, this is one. This is like this. Right? It is joined like this. So you are pulling it, it will snap. So in this way, you can determine the strength. So you are pulling it, it will snap. Okay. Okay, so this was all for today. So we will end today's discussion now. So if there is any doubt, you can mail me or contact me anytime. And as you all know, this video will be up, this PPT, this PowerPoint presentation will be uploaded and the link will be shared. Okay, so thank you and have a good evening.